Hey, what's up YouTube? So here we are back again for some more HVAC Optimal Start Math Playground. Like I've been telling on every video here, we're studying mechanical engineering theory. There's mathematical models defined in research that run on building automation systems, and you pass in zone temperature information, other telemetry of the HVAC system from the building automation system, and the set points that the building automation systems are running, and schedules for the HVAC. And these different models will output minutes to warm up or cool the HVAC, to recover the HVAC zones. Once again, these are energy saving strategies, and typically these models, the code that we're experimenting with in Python form, runs in firmware in the building automation system. But these models are enhanced versions that more than likely are not in building automation systems yet. They're theoretical enhancements that industry could use. But that doesn't, so the building automation systems may not be using these anytime soon, but IoT platforms where IoT practitioners are much more advanced and evolving much more faster than operations technology or building automation systems. So IoT people can be running with this right away, and maybe 10 years into the future, who knows, maybe the building automation industry will adopt it. Building automation technicians don't code. They're typically like an IT person, like a network engineer, maybe in IT, that they use platforms that have GUIs. Like if you were setting up a router, you just have like a GUI, and you're setting up this device and rules and IP addresses, and you're not coding, you're just configuring. So that's what building automation system technicians do, is they're just configuring something that the manufacturer provides them, and these these mathematical models will be embedded in firmware. So there's all these different models. So we're on day 34, which is model 4 through the course. Just 15 more days to go. Once again, read the paper. It's inside the PNNL directory for Pacific Northwest National Labs. They're the group of people that did the optimal start strategies. They ran it on heat pumps, but it runs on any kind of HVAC. Can save 2 to 5 kWh per day per unit. This could be totally different, but it's a really very strong energy saving strategy, but one that's very hard to implement. Most of the time it gets missed, and it's too hard to implement that people just skip it. Because there's not enough faith in these mathematical models. People complain, and then the building operators just end up running equipment probably twice as long as they have to, so people don't complain. Okay, so a little bit about the paper, resistive capacitance models. So we did model 1 already. We also created a model 0 with these efforts, that is just a linear degree per minute model. So it's just calculating recovery rates, that when we start the HVAC, how long does it take in degrees per minute for the zone to reach set point. That is a very early videos. We decompiled the Niagara building automation optimal start, and that's what is running in there. It's very primitive linear model, and some of these other models can outperform it. Model 1, which we've covered before, is the quadratic regression, where it's taking that zone temperature and set point deviation as a quadratic regression formula with this little minutes adder, where in the tutorials we've solved the regression and created an equation. Model 2, which was actually model 0, the linear degree per minute, and then there's also like a weather ratio So this model incorporates outside air temperature. And model 3, this is a multiple linear regression model. Also incorporates outside air temperature and temperature zone set point and temperature deviation. There's also outside air temperature factored into this equation. This was the model where we did some of the matrix algebra by hand, computing the multiple linear regression. And then also we're on model 4, which is a simple first order model. The first order simple physics driven model to predict response time. It's kind of cool. It's the model that I iterate through the recovery data, and then it uses like a little bit of log mathematics to compute this recovery time. So before we dive into our math lesson for today, let's see, so we were on day 34. I just closed the window accidentally. I am making, before we get into this, I am making another YouTube course, hopefully this coming summer. I'm already kind of doing the AI generated coursework. So far we're up to another 57-day challenge. So this is all about data modeling, brick and ASHRAE 223P. So we'll do 20-minute lessons in Python, the same format for graph and RDF theory. It should be really cool because I have been exploring graph, and I have been exploring on the Backpipes 3 repo, the Python backnet stacks. There is a discover objects to RDF, which is the underlying, it's a framework used for graph theory, that we can discover a backnet system to a RDF graph model. And then that's where we would hit the ground running, enhancing these data models after a couple weeks of just what RDF and graph is. Sparkle queries, which are the underlying querying, how to query for the data model, and then a little bit on brick and ASHRAE 223P, and then hybrid models. And what I'm really interested in is doing like a little bit of algorithms, data model based algorithms in Python, and maybe some easy fault detection too, where the fault detection would run across the data model. So that's coming up. I'm excited, and now I just have to get through this, the last 15 days of this. So just like finishing a game of Monopoly, for me this stuff is hard to finish because there's so much more interesting topics yet to explore, but let's try and crank this out. Okay, so I got VS Code open. Okay, day 34, coding model 4. Implement the log formula safely. Implement model 4 requires careful handling of logs. You must avoid taking that log out of 0 and negative numbers. Makes sense. If the delta temperature, which is the zone and temperature difference, is within deadband, you can return 0. Apply this concept above using the formula or algorithm provided. Refer to the mini examples below for demonstration. So here is, this is our, looks like our AI generated code snippet here. It's just, pretty easy. That's our math equation from the paper. And it looks like it wants us to explore just running the code. Seems kind of simple. The previous tutorials on YouTube, like this was our deadband temperature right here. This is our delta T. Wait, I'm sorry. This is delta T. This is deadband. And then this is our decay rate, our alpha C parameter. So the previous videos we went into detail in Python lessons on how to iterate over that saved data structure of the we were calculating we were capturing the zone recovery rates, and then we use that first order iterative least regressions way to calculate this decay rate. So this is just fake data. They're just giving it to us. I'm just gonna get out of this. See what we got here, see if we can plot this fast. Okay, so it's just giving us 10 minutes is if this is a real system, our equation is calculating 10 minutes. And this would obviously depend on real data, real physics, and that crucial decay rate calculation, where before we were plotting it, and that decay rate kind of has this curve to it, like exponential looking quadratic curve, not just a straight linear curve, but that curve, exponential curve. Modify the function to handle heating and cooling modes separately with different deadbands. I don't think in the real world that there would ever be different deadbands. We never program buildings with different deadbands for heating and cooling. That might be a place where AI is currently hallucinating a little bit, but even at current energy code requirements, it's always a fixed deadband. All right, should we actually do this or not? So I think you would calculate this as, let's see, our zone, let's pretend our zone temp is 60 degrees Fahrenheit. Zone set point is 72. So our delta temp would, okay, so I think we could calculate this. Oh yeah, we should just define a delta temp as a good practice. Python, you don't need to define your variables ahead of time. If this was like C++ or Java, we would have to say delta temperature is a float, and something like that. But we should just define it in Python ahead of time, and then you could say if zone temp, we should say if zone temp is less than zone set point, that means, I'm just going to say heat. We could calculate zone, our delta temperature would be delta temp would equal trying to just do this minus zone temp. Also, it would be a heating or cooling application. Else delta temp equals zone temp minus zone set point. I think it's just to keep the value. I think you could just take that absolute value too, but you could even do separate numbers here, even separate decay rates for heating and cooling applications, because the recovering a zone for heat or for cooling will be different loads. So the amount of energy you have to put into the building to remove the heat for cooling or put the heat back in for heating will be different rates in like kW per hour or BTU per hour. So we could just say maybe we should just put delta t, delta t, delta t. And we could even just remove that from here. Way it's being defined. Now whatever. So at the moment for heat, we'd be heating. So now we calculated some different metrics because our delta temperature is much different. Hopefully that makes sense. What happens if you pass a decay rate of 1? I think you divide by 0, which will not make the last point. Yep, divide by 0. Yeah, you can't take, yeah, divide by 0. I have to think about that. The log of 1. Anyways, divide by 0 error. Integrate this function into a control loop. I don't think I'm going to spend a lot of time on this, but like I just cheated and used AI for this. So let's just run this. This is something that's kind of cool. I think you can do with AI is just make little simulations like really fast. So as you can see, like it's just stepping through some mini simulation here, and as soon as it hits the deadband, I think it should, yep, okay. So this is probably what it would kind of look like in the real world. So what the initial temperature was 61 degrees Fahrenheit, our delta temperature is 12, and then this is this looks kind of funny because like I don't think in the real world we would be running this calculation every step in here. I think that we would just be calculating, running our model once, and then we would just be sitting and waiting until that, until our countdown is true. So here, let's just, this is the heart of the computer science part of the optimal start. So I'm just going to chat with ChatGPT, say, can this be refined? What I want to see is the minutes to recover the zone is calculated just once. And then the simulation should mimic prior to occupancy if the minutes calculated to recover the zone is less than the actual minutes to zone occupancy, then start the HVAC early, else it should sleep or wait until modeled minutes to recover is less than actual time to recover the zone. Okay, let's see what this I think AI is kind of nice to do these little simple simulations, and like the thing that we found wrong is like it was constantly predicting the model, the minutes, and like in the real world I think we would only want to do that once. So like let's say it's our building is set to occupy at 7 o'clock in the morning. Maybe at 3 o'clock in the morning we run our model, predict our minutes. 4 o'clock in the morning we update it. 5 o'clock in the morning, and then as we get closer to that time that we're ready for the building to start to warm up, to require it to warm up, then we should be kind of fine-tuning it. All right, let's see what this looks like. get our AI generated code, and then us, the humans, will just validate that it's correct or not. Oh, this is funny. I don't know what it's doing here, but this is kind of interesting. So it's simulating the zone is warming up. Okay, so what is it doing here? So it's currently 60 degrees Fahrenheit, set point of 72, our delta temp of this. So our model is 60 minutes till occupied. So the model force says we need to wait 24 minutes to reach a deadband of 0.5. I'm just going to say move this to 5.0. This would be actual energy code required deadband. Let's see what our simulation does now. Sometimes that AI generated code can be a little bit funny. So we reached our deadband in 7 minutes. Actually, I'm going to say this would be 2.5. I don't think this is a real deadband, because to me a deadband of 5 degrees would be 2.5 degrees above and then 2.5 degrees below, but this is actually looked like it's subtracting a full 5 degrees plus or minus. So all right, so let's see, not really sure what this does, but so our model is predicting 12 minutes to reach a deadband of 2.5 degrees if we're at 60 degrees, and we're just simulating that if the building is occupied in 60 minutes, which our code would be looking at that, when the building is occupied 60 minutes into the future, then our model is predicting we need 12 minutes, so we would sit and wait until right up to that, if our building is set to be occupied in 13 minutes, then we would pretty much start our HVAC system, because our model says we need 12.27 minutes. So hopefully that makes sense. And what it attempted to do here, so it's this is what we would expect to see on the real life building automation system, is that we started our HVAC system, and then it's slowly warming up, and then we reached our zone set point. Hopefully that makes sense. It's kind of confusing what it did here, but this would be kind of like what we would be coding in the real building automation system, that we're constantly looking at when is the building occupied into the future, and then comparing it to our modeled minutes. And then when the actual occupied time is less than the modeled minutes, then boom, that's when we start our HVAC system. And it's optimized to a point that we're trying to save energy. So I think that is probably enough for this video, even though we could probably, I was going to try and do 2 of these examples. So, all right, maybe we could just do this one too, because it looks like week 5 in review. This is the last day. At this point, you have learned a linear model, quadratic model, the weather adjusted 2 model, the log model, model 4. Each model adds its complexity. So here we go. So let's just run this real quick, and we can just get out of here, just import math. So whatever it's doing here, so this is, I can tell right here, this is model 0, because it's just a delta t behind a rate. This is model 2, I think. Here's our quadratic model 1, model 2. So anyways, I don't think I'm going to spend much time on this one, because we've covered these models in details on previous lessons. So the only thing that makes me think about is if you read the paper, which I highly recommend doing, the paper goes into great detail on which models performed better in some scenarios. For example, like it talks about model 1 works well on like zones that are not really affected by like an exterior wall. That's where they liked model 1, and then they actually liked model 3 the best, were zones that are probably outdoor zone, and the weather is really affected by this exterior zone. I think that's all I'm going to say about this. And then model 4, I actually think this model 4 is kind of cool. That I think that basically this log and iterative model that may not work for really big delta temperatures. Like if there's like really small delta temperature required, that's where I think this decay rate, this iterative approach may actually perform better than kind of this linear guess. So, but read the paper. It goes into detail, great detail on each model, and then like the research that they conducted on which model can perform the best. And I think that's all I'm going to say, because our what we're doing here is just attempting to learn how these models work in pseudocode format in Python. So I think that's all I have for today, folks. So thanks for watching. We'll get back on day 36 tomorrow. Have a good one.